Thank you very much, Professor Chatterjee and Professor Mukunda. I came to Bangalore, I think as Professor Mukunda just mentioned, during my last year of PhD at Chicago. At Chandra's recommendation, I spent a whole quarter here, spent between the CTS, the Center for Theoretical Studies, at this institute, and the Raman Institute. And I have the fondest memory of that time. So today I want to tell you about this general relativity and its discovery and how it has evolved. Now, generally when one gives such public lectures, one usually focuses on some recent development, exciting advance that has occurred in science, and spends time explaining it in general terms to a wider audience. Well, but from time to time, it is sort of, it's good, I think, to change this style a little bit and take a subject like general relativity and give a perspective which is very, very broad, right? Basically, advances that occurred over 100 years. And as we'll see, this kind of a perspective tells you how nonlinear the evolution of science is. Particularly to the young people in the audience, and there are many of you here, I'm very happy about that. Many of the things that you hear today and you study today may seem like obvious to you and may seem like it was always so. And we'll see that that is not the case. You will see that big mistakes were made and then they actually changed, then they were corrected, and these corrections changed the course of science. I find that even for myself, as a senior researcher, such broad perspectives are also useful to sort of say, provide a campus, because sometimes you are so involved in your work that you don't have this broad perspective about how science actually evolves, and that actually can make you reformulate your broad research goals and interests. And so I hope that this goal is my goal, and I hope it is okay with you. Then, let me then begin. Basically, in this talk, what I want to provide you with is a bird's eye view of the discovery and the deep impact of general theory of relativity. Well, I will only be able to focus on what is called classical general relativity and not the quantum aspects of the theory, which are dominating in the last many years now, maybe 2 or 3 decades now. Actually, Mukunda mentioned about this Dirac's theory of constraint systems, and that was actually a beginning of this quantum theory of gravity. But I gave a colloquium this morning on that topic, so I don't feel too bad about missing it out. And even in the classical theory, I'm only going to provide you with an impressionist portrait. The talk is in 4 parts. First, I will tell you what general relativity is about, how it was discovered. Then we'll see that general relativity led to the cosmology, what we today call about the science of the large-scale structure of the universe that originated with general relativity. Then I will tell you about black holes, and then I will tell you about gravitational waves, and then summarize. Okay, so let's begin with the history. How was general relativity discovered? As you all know, in 1905, Einstein discovered special theory of relativity. At that time, he was still working in the patent office as a clerk. And in 1907, he was still in Bern in the patent office. And he was asked to write a review article on special relativity. And this was for a journal, which was annual reviews kind of journal, from Göttingen. And Einstein, there is a very moving letter that Einstein wrote to the editors, saying that, well, since he works in the patent office, he's off only at 5 o'clock, and by 5 o'clock all the university libraries close. So he has not been able to keep up with the literature. He doesn't know what exactly happened in the last couple of years. So could they provide him with some of this literature? It's a very beautiful, moving story up here. But when he was started writing this review article, he realized that there is actually a tension between special theory of relativity and Newtonian gravity. Professor Mukunda mentioned about Maxwell's discovery of unifying electric and magnetic forces. And then it really was a tension between the electromagnetism and Newton's notions of space and time, and that tension was resolved through special relativity. But then Einstein realized that there is a new tension. Einstein changed the notions of space and time in special relativity, and in special relativity, distance simultaneity of events does not make any sense. There is no absolute time. Time depends on the state of motion of observers. But in Newtonian gravity, as you know, if I look at this pointer and if I move it, then the gravitational force exerted by the pointer at the back of the room, for example, is propagated instantaneously. And that is not compatible with special relativity. So Einstein began thinking that we need a new theory of gravity. And therefore, he wanted to know, in fact, to resolve this tension, should we actually change our notions of space and time and of gravity once again? Einstein was continued to think about this in a single-minded way. And in 1913, by then Einstein was professor at the ETH in Zurich, and Max Planck, who was founder of quantum mechanics and senior German physicist, came to Zurich to convince Einstein to move back to Germany, to Berlin, and they offered him a very nice offer with 3 positions at the same time and so on. And all this administrative talk was first conducted, the terms of the offer were explained to Einstein and so on. And when this was done, Max Planck asked Einstein, so what are we now working on? So Einstein said that he is looking for a new theory of space, time, and gravitation. And Max Planck's response to that was, as an older friend, I must advise you against it. For in the first place, you will not succeed. And even if you did succeed, no one will believe you. And this is coming from Max Planck, not some random person. It's a senior physicist up there coming from that. So this shows how ahead of time Einstein was, how much, even leaders in physics were kind of completely unaware of it. But fortunately for us, Einstein persisted, and 2 years later discovered general relativity. Oops. Good. And then the final paper Einstein sent to the Academy, the Prussian Academy, on the 26th of November. And on the 28th, he wrote this letter to Arnold Sommerfeld, who was, the eminent theoretical physicist. 8 of his students got Nobel Prizes. He himself was nominated a couple of times. And Einstein wrote to him, as was said by Professor Chatterjee, this really is a hard subject. And Einstein had to exert himself enormously for 8 years. And particularly the last couple of months, he had heard a lot. He had worked extremely hard. And he said, during the last month, I experienced one of the most exciting and one of the most exacting times of my life. True enough, also one of the most successful. And Einstein discovered the final form of the equations of general relativity and then applied it to a problem that had been opened. And the problem had to do with the motion of Mercury. There was a certain anomaly in the motion of Mercury that had been known. It was very tiny. It was only 43 minutes of an arc per century. But it was well established, and Einstein found, to his delight, that when he applied equations of general relativity to the motion of Mercury, he found he could account for this discrepancy. In other words, he could account for the observed value. So Einstein was very excited about it, and he wrote to Sommerfeld then. So what is this beautiful theory of Einstein's all about? So let me have just a summary in one slide of general theory of relativity. So the basic idea is the following. See, people started thinking about space and time long time ago. I mean, Buddhist literature, Hindu literature, Greek literature has sort of treatises on the nature of space and time. But for those 2,500 years, space and time was always an arena. It's like a stage on which things happen. The stage is not an actor. Right? Stage is just sitting there, and things happen in the stage. So geometry of space and time was just a stage on which things happen. Planets moved, electromagnetic fields propagated, and so on. Well, with general theory of relativity, that changes. Space and time becomes a dynamical entity. It becomes like this pointer, or like those chairs. It can be acted upon, and when you act upon it, it moves, it changes its state, and it reacts back. So space-time geometry becomes a dynamical entity, like all other dynamical entities, physical entities, that we are really aware of. So why does this occur? It is because the gravitational field itself, that the Newtonian idea of gravitational field, so to say, disappears in a certain way and is encoded in the very geometry of space-time. So if you have a massive object like sun, it bends space-time, it walks space-time around it, it bends it, and so to say that bending encodes the whole effect of gravity.
And then when test bodies like the Earth move around it, small other bodies, if you like, in a literal sense, these bodies in space and time try to move as straight as they can, so-called geodesic paths. But from the Newtonian perspective, these paths look like ellipses, the Newtonian ellipses in space. So in the space-time description of Einstein's, really everything is encoded in this bent geometry. Now why is this possible? Why is it that gravitational force can be incorporated into the geometry of space-time and not, for example, electromagnetic force? It is because gravity has two characteristics which are unique. First, it is omnipresent. You see, I can build cages, I can build these rooms where there is no electromagnetic field at all, basically because we have got both positive and negative charges. But there is no place in the universe where there is no gravitational field at all, because there is always mass, and there is only one sign of mass. And there is always gravitational field everywhere. So it's omnipresent, just like space-time geometry, which is omnipresent. And the second thing is that it is non-discriminated. It acts on everything exactly the same way. Doesn't matter whether it is copper or gold. Doesn't matter whether it is positive charged particle or negative charged particle. Doesn't matter if it's a nuclear particle with certain quantum numbers or another nuclear particle with other quantum numbers. Gravitational field acts on them exactly the same way, just like geometry. And that is the reason why gravitational field, and only gravitational field, can be absorbed into the very geometry of space and time. And then matter, as like the sun, for example, tells space-time how to curve, and space-time tells matter how to move. The geometry is intertwined with matter via the equations that Einstein discovered. So this was a really fabulous idea, you know, right? A totally, completely different kind of idea, and changed the perspective entirely. And this was recognized quickly by the towering intellectuals at the time. Hermann Weyl, a leading figure in physics and mathematics both, wrote one of the first books on general relativities in space, time, and matter. So here is a quote from Hermann Weyl. He says, "It is as if a wall which separated us from truth has collapsed. Wider expanses and greater depths are now exposed to the searching eye of knowledge, regions of which we had not even a presentiment." It is as though we are all enclosed in this room and the curtains were all drawn and we are just accustomed to this room, and suddenly the curtains were open and out there was beautiful vistas. Suddenly we became aware of it. So that is a sentiment that leading people had with Einstein's theory of general relativity. And here is a beautiful quote from Chandra. It refers to Henry Moore. Henry Moore was one of the leading sculptors of last century. His sculpture, Atomic Energy, is on the campus of University of Chicago. And Henry Moore visited University of Chicago. So Chandra says, when Henry Moore visited the University of Chicago some years ago, I had the occasion to ask him how one should see sculptures. Now those of you who know Chandra can appreciate that only Chandra can ask such questions, right? How one should see sculptures. Should one see the sculptures from far, or should one see them from nearby, from close? And Moore's response was, the greatest sculptures can be viewed, and indeed should be viewed, from all distances, because new aspects of beauty will be revealed at every scale. And he gave an example of Michelangelo, and this is La Pieta of Michelangelo, which is in Vatican. And in the same way, now Chandra says, the general theory of relativity reveals strangeness in proportion at every level in which one may explore its consequences. This phrase, strangeness in proportion, comes from William Blake, that Chandra liked enormously, which has to do with what is a sign of true beauty. The true beauty should be a little bit strange, but the strangeness should be in proportion. And this is what Chandra had to say about general relativity. Now, this is all very beautiful, but one might say it's so abstract, right? Space and time bend and curve and all that. I mean, in some sense, why would ordinary people care about it? Why would general relativity become such a sensation that everybody suddenly, Einstein becomes a household name? Well, this happens in a very curious historical almost accident, right? And this is important for people who want to think about science, how science evolves and how things happen. What happened was basically the following. Arthur Eddington, very distinguished astrophysicist in Britain, happened to be also a Quaker, and therefore he was a pacifist opposed to war and violence. So he did not want to fight in the First World War. He was prepared to go to prison as a conscientious objector. But the Royal Society, but the Astronomer Royal thought that this was really, could not really happen. And therefore what he did was to find a mission for Eddington in order to send him on the mission so he doesn't have to fight in the First World War. And this mission was to verify Einstein's theory of general relativity. And this was going to be happening by, this required travel to a certain island of West Africa, where in fact one was going to see a total eclipse. Now why was this important? Well, as we saw a couple of transparencies back, what happens is that if you have a central dense object like sun, then space-time bends around it. Now if I have a distant star and the light is traveling towards me, coming from this side up here, then this light actually goes down and comes back again. And so to me, it appears that the star is somewhere, you know. Now, if this is sun and this is earth, and now if I go up 6 months later, I am on the other side of the sun, facing the star again, then you can see that the light is going to not go through this curvature of sun, and therefore the star would appear to be somewhere else. So by observing the star from the two sides of the sun, so to say, one can tell if in fact light is bent according to Einstein's theory. But this of course requires a total eclipse, because one time when you are looking at the star, the sun is right in front of you, and of course you have to face the sun because the star is on that side. If you face the other way around, then you're back towards the sun, then you don't see the star. So you need a total eclipse there, and that's why Eddington could go and was sent on this mission. He did go there, and he confirmed Einstein's theory of general relativity. Those of you who are experts in the subject may have heard that a lot of people thought that Eddington's error estimates were not correct, and so on. As it happens, just in the last couple of years, real experts have gone back and looked at Eddington's data, and that confirmed that what Eddington said was really true. This is just a side remark for you. Okay, so this is what happened, and then suddenly Einstein became a household name. Why? Well, we were at the end of the First World War. The world was tired by human stupidity, all this violence, all these divisions between countries and so on. And here was science, which came and stood away like a tower, like a beacon of light, which was away from all this stupidity. A theory which was discovered in Germany by the German scientist Einstein during the war was verified by British astrophysicists, the other side of the war, so to say, and was confirmed. And so overnight Einstein became a celebrity. Here I just happen to have the cover of New York Times on 10th November 1919. And the headline says, "Lights all askew in the heavens. Men of science more or less agog over the results of the eclipse observation. Einstein's theory triumphs. Stars not where they seem to be or were calculated to be, but no one need worry." So this is what happened. I mean, suddenly Einstein became a part of the general culture. So this is how, often this is not related to hard science, but we are human beings. Science is part of the human endeavor. So this is all beautiful, and Einstein's theory is fantastic, and it all works. But as Professor Chatterjee felt, that this is an esoteric theory, right? So most of the theory says, yeah, that's all very beautiful, but what does it matter? I mean, what is the practical use? Well, I think that this theory offers a very interesting lesson for all of us. Namely, fundamental laws of nature always matter. Why? An outstanding example is the global positioning satellite system that we use in our cell phones every day. Absolutely every day. Cell phones would not function because of that. There are a bunch of satellites. They are sending light signals, and because there are several of them, they track your device, and because there are several of them, they basically provide coordinate of where you are. Right? But in order to do that, these clocks on these satellites have to function properly. Now it turns out that because the satellites are moving, their clocks tick at a different rate than your clocks on Earth. But also because satellites are high up, where the gravitational field is weaker than where we are, because of bending of space and time, the clocks tick here at a different rate. It's a physical fact. Clocks tick here at a different rate than they tick out there. And you have to take into account this effect. If you did not take this into account, then in fact you will get errors. And one would say, oh, yeah, that error may be like 1 millionth of a second in 100 years. No. that error is huge. If general relativity and special relativity were ignored, then within 2 minutes, the GPS accuracy will fail sufficiently for today's airplanes to land on the airspace. So bent space-time affects you every day. That's the basic lesson I want to tell you. Those of students who are interested, you can just Google this fact by going to Clifford, C-L-R-F-F-O-R-D, Will, W-I-L-L, and GPS, and you will find the explanation about how these 2 minutes come about. Okay, so this is the end of the first part. Now I would like to tell you about the second part, which has to do with cosmology. As I said, cosmology began, its birth, modern cosmology began really with a general theory of relativity. Now, as you all know, Newton had this audacity, had this intellectual arrogance, if you like, to think that a laws which govern a falling apple on Earth is also the law, are also the laws which govern the planets moving around the sun. That there is no distinction between the two. Something that we see on Earth is the same as what is happening in the heavens. Remember, you have to go back in those times when most of the people believed that the planets were moving because angels were pushing them. Right? So this is daring, right? And this is the kind of paradigm shift that occurred. Well, Einstein's daring was even bigger. He thought that you could take his field equations and apply them to the universe as a whole. Not the planetary system, but the universe as a whole. Now, imagine, it's only a few years before that people had realized that Milky Way is not the whole universe, that there are also other galaxies. And what Einstein did was, literally took his equations and solved them. Just as Newton modeled the planets and the sun as point particles, which seems ridiculous when you first think about it, and they solved the equations, Einstein took the galaxies as dust particles. And the only force between them was gravitational force, relativistic gravitational force, and used these equations to see what happens. So that was a daring idea, that one can actually take these laws of general relativity and apply them to the universe as a whole. And now what happens is the following. So first let me tell you the story, and then tell you the history. In other words, the final answer is this, and then we'll tell you the story about how we arrived at the final answer. Basically, the evolution of geometry is quoted by Einstein's equation, and Einstein's equations tell us that space-time curvature is equal to 8 pi g times the matter stress and rate tensor. One uses Einstein's equations, and one uses an observed fact that if you looked at the universe at sufficiently large scales, then there is no preferred direction in the universe, and there is no preferred place in the universe. The universe is isotropic and homogeneous. If you put these two assumptions together, you immediately conclude that geometry must be dynamical and should be related to matter via Einstein's equations, and therefore we have got the standard picture that there was a Big Bang and the universe began with a primordial explosion about 14 billion years ago. Now, to students and so on, they have learned this, and there's a fact. It's as boring as the fact that the sun rises or something like that. This just is not true. No, it was never like that. It really took a long time to come to these conclusions. Why? Well, a year or 2 years after Einstein discovered general relativity, Einstein and de Sitter solved these equations and tried to construct models of the universe. At that time, Einstein believed that the universe is not time-changing, it's not expanding. So he introduced, for those of you who know, a cosmological constant term, his equations. And then the idea was that here is time and here is space, and the universe is just like that, nothing is changing. And basically, the gravitational attraction in this model is balanced by a repulsive force, effective repulsive force of a cosmological constant, so that the universe doesn't change in time. So there is matter and the cosmological constant here. De Sitter found a solution of Einstein's equation, also with cosmological constant, in which there is no matter at all, and therefore the universe sort of comes in like that and goes out like that. So the spatial volumes are decreasing, and then they are increasing up here. But in 1920 to 24, Friedman, a Russian mathematician and astronomer, just took Einstein's equations without a cosmological constant and solved them, and found that there are solutions in which the universe is expanding or contracting. So he looked at the expanding ones, for example. Then the picture doesn't look like this. Picture looks like this. Time is running like that, and this is space. And the space is expanding out of here. So if you go back in time, space is contracting, and you go back and back and back, and an instant comes when Einstein's equation tell you that the space-time continuum tears, and if you like, this is the Big Bang, where there is a sort of a singularity in which, according to classical general relativity, the physics stops. This is where we need quantum theory of gravity, and this is what my talk in the morning was about. How do you go beyond that in order to do physics using quantum physics? But this was what was happening with Friedman. But Friedman sort of treated it as a mathematical problem, as though he did not really believe physically this happens. He solved Einstein's equation with positive energy density, with negative energy density. He did all those things. Lemaitre, on the other hand, was a Belgian Catholic priest. He was a Jesuit. And he took Einstein's equation, he solved them, and he really took everything very seriously. He did think about the galaxies as just particles. He really thought astrophysically, and he really did think that there is a singularity, and the theory really completely breaks down up here. Lemaitre was remarkable, and I think is not enough recognized even now. I mean, he did get lots of honors and so on, but I think he was really seminal in all these discussions. So, but nonetheless, so this happened in the 20s, but nonetheless, in 1930, there was a meeting of the Royal Astronomical Society in London, at which Eddington, who was the president of the society at the time, sort of raised the question, saying that, well, we only have these two models. He completely ignored this altogether. Only these two models, and then shall we actually put some dynamics into this model? It is static, that's kind of boring. Or shall we put some matter here and make it a different model? So Eddington's question, in his typical fashion, he asked the question, shall we put a little motion into Einstein's world of inert matter, or a little matter into the de Sitter premium mobile? Because the premium mobile, because there was no matter, it just came, contracted and expanded by itself. Well, it turned out that Lemaitre had already solved the problem. Lemaitre knew Eddington because he had spent a year in Cambridge. And Lemaitre wrote to him, he said, but I've already solved this problem. And, I even sent you the paper. And apparently there was one instance in which Eddington was shamefaced, according to Macria, who was a student of Eddington's. And then Eddington quickly recognized that Lemaitre was right. And then a year later, Hubble's discovery came that the universe is actually expanding, and then the statement is that people sort of quickly converted over. Einstein removed his cosmological constant. There's another story about Lemaitre. Namely, Lemaitre went back and told Einstein, don't make it an aesthetic consideration. It's a physical question, if there is a cosmological constant or not. Whereas Einstein always thought it was an ugly thing and had to be removed and so on and so forth. And today we know Lemaitre was right. So he corrected Eddington, he corrected Einstein, and he corrected the Pope. So what happened is basically that in 1951, George Gamow, I'll tell a little more about Gamow, actually had discovered this thing of nuclear reactions and so on, and come to the conclusion that the universe must have begun with a hot Big Bang. And then he wrote to the Pope Pius. Gamow was a colorful character. By the way, I owe a great deal to Gamow because I got interested in physics and cosmology and such things, reading his popular books. So in the high school, I read his 1, 2, 3 up to infinity and such things. He was a very colorful person. So he wrote to, I don't think he was religious at all, but he wrote to Pope Pius XII by just saying that, well, look, just like science is also saying that the universe has finite beginning. Pope Pius XII was excited, thinking that science and religion are coming together, and there was an astronomical meeting. Vatican has an observatory, and therefore there were astronomical meetings there. And that meeting, he sort of, said, well, science and religion are finally coming together, etc. But Eddington Lemaitre had the audacity to go and correct the Pope by telling in a private audience, sort of convinced him that one should keep religion and science separate. And indeed, someone must have convinced him very well. Well, after all, he was a Jesuit, so they know how to convince people. So he, and the Pope then, there was a much bigger meeting, astronomical meeting next year, and the Pope never mentioned this again. So there are interesting episodes that happen. But really, for the longest time, whether to believe in the Big Bang theory or whether not to believe in Big Bang theory was really kind of remained an aesthetic preference, philosophical aesthetic preference up here. There was a program in Soviet Union led by Lifshitz, Landau Lifshitz, and Kalashnikov and others to say that, well, this Big Bang was an artifact of high degree of symmetry. if you have realistic solutions of Einstein's which don't have a symmetry, there would be no Big Bang, there would be no singularity. This was shattered by the singularity theorems that were proved by Roger Penrose, and then after that, the whole, this program basically didn't continue. But then something else came, which was the steady state ideas that were put forward by Fred Hoyle, J. Narlikar, Hermann Bondi, Tom Gold, Dennis Sharma. So these people had this idea. These are the leading minds at the time, and they were convinced that, in fact, that the idea of a Big Bang was not something that's very good, and one should really be talking about, one should not be talking about a Big Bang at all. In fact, the name Big Bang was coined by Fred Hoyle to make fun of the idea. Now it is stuck, but it was supposed to be a pejorative term, a sarcastic term about this idea. So this is what happened, except that finally there was a transition from mathematics and aesthetics to physics, and this happened because of two things. The first was nucleosynthesis, the second is the cosmic microwave background. So the nucleosynthesis issue is the following. See, we're all made of atoms right here. So where did these atoms come from? I mean, most of them are quite heavy atoms, and where did this heavy atom come from? Well, these are cooked in stars. Stars are ovens which cook these atoms through nuclear reactions. But if you look at more carefully, that's what people did. Hans Bethe and George Gamow, Alpher, and so on. They did this very carefully, and they found that if you look at the light elements, particularly helium, hydrogen, lithium, then their abundances that were observed were such that they could not have been cooked in stars. They were cooked earlier on. They were already there before the stars were born. And so the question is really, how did they arise? How did these elements arise? So then the idea came that there must have been some hot early epoch, and then quickly George Gamow realized that this must be the Big Bang model, very, very early universe, where the universe was hot, and that is where the light elements were actually cooked. And it fit together very, very well, and it's a very detailed theory. So it fit very, very, very well up here. So that sort of gave some lot of credence to, in the physics community, for the Big Bang model. Then there was the issue about cosmic microwave background. So basically, what we see where the whole universe is bathed in these electromagnetic waves that are all around us. They are basically like a black body radiation that surrounds us. And if in fact there was an early epoch of a hot Big Bang, then there is a natural way for this cosmic microwave background to have come about. Basically because at the very early time the universe was very hot, atoms couldn't form. As the universe expanded, it cooled down, and the first hydrogen atom could be formed, and then so to say the matter decoupled from the radiation and could flow towards us, and that is the cosmic radiation that we see today. So these two factors brought the Big Bang to the mainstream picture. So here is the cosmic microwave background, and here is the snap. Basically, this is time, this is space, and the idea is that we are up there, we're looking back, and we find this glow, if you like, afterglow of a big bang, if you like, that we see up here, hot universe, early universe. And so this is really a snapshot of the universe when it was 380,000 years young. So this occurred quite a long time ago. Today it's about 14 billion years. This happened when the universe was only 380,000 years young. And there is a spectacular success over the last 2 decades. People have observed this microwave radiation. This microwave radiation has slight fluctuations. And this say that the density was not completely uniform. It was almost uniform. But there were fluctuations of the order of 1 part in 100,000. And these fluctuations in density grew because you have matter is attracted towards higher density because of gravity and goes away from places where there is less density. And this leads to basically the large-scale structure. And the cosmic microwave background has been observed very carefully through these 3 generations of satellites. The first one was called Kobe, a cosmic microwave background explorer, launched in 1989. It was followed by the Wilkinson microwave anisotropy probe. It was launched in 2001. Basically, in going from here to here, the error bars reduced so much that the parameter space of cosmology shrunk by a factor of 30,000. And then there was a similar huge jump in the precision the next time when, in fact, the Planck satellite was released in 2009. They released their final data a few months ago, and they're still going to release a little more data in the next year or so. So these missions are so incredibly accurate that given us a picture of the universe, very, very early universe, so well that in fact we understand we understand quite well now the origin of this we understand quite well the nature of the cosmic microwave background. So basically, when the universe was 380,000 years ago, the universe was extremely homogeneous, as Lemaitre had envisaged, and in today's terms, the temperature is about 2.73 degrees Kelvin. So here is a black body curve, which is you see in textbooks, and these are the observations. You can see that the errors are so small that, in fact, you see this black body curve very, very well. But nonetheless, there are some of these tiny inhomogeneities, which are 1 part in 100,000. And then what happens is the following, that these tiny inhomogeneities seen in the cosmic microwave background, with the universe was about 380,000 years young, grew because of gravitational attraction, obeying equations of general relativity, and knowing the known physics, the dynamic astrophysics, gastrophysics, one can actually show that these fluctuations grow to give us the large-scale structure of the universe we see today, some 14 billion years ago. This is the true trial, you see. So if you look at 380,000 years, and if you divide by 14 billion years now, that is, in human terms, like a ratio between 1 day and 100 years. So what the command of physics we have today, astrophysics and fundamental physics we have today, is such beautiful, it's so much is the following. Namely, in human terms, basically, if you were to take a snapshot of a baby, when the baby was 1 day old, and then I got a theoretical understanding completely, I put it in the computer program, all the laws are known in biochemistry, biology, molecular biology, physiology, and so on, as to give me the portrait of the person when the person is 100 years old. Imagine how much you would need to know. We know that for the universe. This baby grew to this height. So it's really very spectacular. I was going to say a few more things about cosmology, but given the time, I will just skip the last part, which is equally exciting, but I'll just skip that and go to the black hole part. So now let me tell you a few things about black holes. So as you know what black holes are, they are regions of space-time from which even light cannot escape. So here is a portrait of cartoon of a small black hole, a few solar masses black hole, and it is gobbling up a star, and as it gobbles up the star, it spews out these huge jets, which are actually seen in observations. And now, therefore, black holes, these small black holes, are widely regarded as the engines that drive most energetic phenomena in astrophysics. Small black holes, I mean a few solar masses black holes. These are widely regarded as. In our own galaxy, in the center, there is a black hole. How do you know it? Well, we look at there is a central region. Of course, we don't see anything there. But we see that the stars are orbiting around it. And as though there was a high mass in the center. And by looking at these orbits of the stars which circulate, and they have been looked at for 15 years or so now, carefully monitored, and one concludes that there must be a mass of about 4 million solar masses in the central region, and this is our own black hole, Sagittarius A star. Right? This is the black hole that we have. These are the large black holes, like million solar masses. Now, as early as 230 years ago, as early as 1784, there were ideas about black hole already using Newtonian gravity. And here is a quote from the Philosophical Transactions of the Royal Society by John Mitchell. He calculates in Newtonian gravity that you might have a body such that the escape velocity from that body equals the speed of light for that body. And then even light would not escape, therefore they would appear as black. And he concludes that if there should exist in nature any such bodies, we could have no information from sight. Yet, if any luminous body should appear to revolve around them, we might still, perhaps, from the motion of these revolving out bodies, infer the existence of the central ones with some degree of probability. And amazingly, that's what we're doing with our Milky Way today, right? It looks very prescient up here. And then same thing is true with Marquis de Laplace. Wrote this famous celestial mechanics volumes in which he calculated, saying that there may be a luminous body of the same density as Earth, whose diameter is about 250 times larger than that of Sun, can, by the attractive power, prevent light from reaching us. Consequently, the largest bodies in the universe could remain still invisible to us. So this is what you hear often, particularly students and so on. Therefore, you might think that, well, black holes is nothing new. They existed in Newtonian gravity. This is wrong. This is wrong for the following reason. That in Newtonian gravity, in all of Newtonian physics, all speeds are relative, including the speed of light. So the speed of light that is used in these arguments is really the speed of light in some rest frame. So one might see it's the rest frame of the central object, not of the object itself, which is supposed to be emitting light. But if I had an object like that, like the moon, for example, sitting out there, and if I shine light on it, as the sun shines light on the moon, light is reflected. So as the light falls in fact, as it falls in, it should be accelerated, and by the time it hits the surface of the object, its just by momentum conservation, this light would be able to reflect back. In other words, because the speed c is relative to in the rest frame of this object, really, you can just do a two-line calculation to see that by reflection of light, such bodies should be actually observable. Or if you want to give a simple-minded picture, you have got such a body in the atmosphere. There will be atoms moving around. Some atoms will be moving this way, emit light. Then the speed of this atom is v, plus the speed of light in its rest frame will be c. So the total speed of the light ray will be c plus v, and therefore it will be bigger than the escape velocity, and therefore it will actually escape from it. So in Newtonian gravity, you cannot have black holes. If you are consistent, you cannot have black holes. So what we need for black holes is both an absolute speed of light, which is independent of any observer, and that is what special relativity gives us. And you need gravity, and therefore you need general relativity. So in general relativity, you can have region of space-time. Time is running this way, space is horizontal, and there will be some regions of space-time like that. If there is sufficient matter in these regions of space-time, then you have got this light cones, which are some of which tell you how light propagates. Light propagates along these cones in space-time picture. So these light cones are far away from the body, would look upright, like in flat space, like if there was no matter at all. But this matter would try to attract, will actually tip these light cones. Light rays will be attracted up here. And a stage comes where all the future directed light rays become trapped in some space-time region. And this occurs irrespective of any observer. There is no relative motion up here. It happens for all observers, and it has nothing to do with and it happens because of strong gravity in this region. So in general relativity, we can have regions in which light is trapped, and in absolute sense, and irrespective of who observes, and curved space-time is really essential for these black holes. Now, I told you about curious history in cosmology, that people took a long time to believe that the universe is expanding, and finally, it's really, but beautiful thing about physics is that you can have philosophical prejudices, and we should have them to drive our work. But then finally, observations come and kill an idea or elevate an idea. There, nucleosynthesis and microwave radiation sort of told us that the Big Bang idea was the correct idea. We did some approximation, it was the correct idea. So the same thing happened in black hole field. Namely, there's a curious history. The simplest black hole solution was discovered by Karl Schwarzschild, while he was serving on the German front during the World War I. So very soon after Einstein's paper came in, it was published before the war was finished. And he wrote from the front lines, letter to Einstein showing the solution. Einstein was surprised that exact solution could be found, but that's what happened. It's an unfortunate thing that Schwarzschild actually died in the First World War because he caught some disease, and he actually died then. But the clear interpretation that this is what represents a black hole, had to await several decades. And I think people in India know very well the Chandrasekhar Eddington episode. Chandrasekhar found that if you have a star which has burnt its nuclear fuel, then it would actually contract. Then it could perhaps reach an equilibrium by balancing gravitation attraction with the Fermi non-degeneracy pressure, because these are fermions, like ideal electrons and neutrons, and therefore that you cannot put them in the same state. Therefore, there is a certain pressure, quantum mechanical pressure, that comes into the picture. However, if the star was sufficiently large, its mass was more than 1.4 solar masses, then gravity wins. The Fermi repulsion is not enough, and therefore therefore the star would actually collapse. But Eddington refused to believe it, and Eddington said such things such as, various accidents may intervene to save the star, but I want more protection than that. I think there should be a law of nature to prevent a star from behaving in this absurd manner. It's a good lesson for young people, namely, don't take seriously if in fact senior people tell you that your ideas are completely wrong, right? Have persistence, but also be very self-critical, right? Chandra did not just say that I am right and Eddington is wrong and go away, but rather he persisted, worked on it for almost 10 years, really developed these ideas in great detail, and then left the subject, right? And of course, as we all know, years later, he won the Nobel Prize for this work. Curiously, Einstein was also opposed to this idea of black holes. So he did a calculation. He took a star or a body with perfect fluid, if you like, and he looked at its collapse under gravitation attraction. But he assumed that the star would contract in what is called as adiabatic manner. In other words, very, very slowly, very, very smoothly. And then he found that the star would not collapse, that this black hole would not form. But it turns out that this assumption was incorrect. So it's like, this calculation was not wrong, but the assumption was incorrect, because when the star goes, it really goes zoop, right? It's a millisecond that it takes for the neutron star, solar mass object, to really become a black hole. And therefore, this assumption was wrong, and Einstein was also wrong. So Einstein thought that it was impossible to form the black hole through gravitational collapse. But just a few months later, people, Oppenheimer, Volkoff, solved this problem and showed that the black holes do form. Curiously, Bergman, as Professor Mukunda mentioned, was an assistant of Einstein, and he wrote this very influential book in 1942 on general relativity, the first serious textbook in English language, if you like, on general relativity. And then, no, that's not true. Eddington had already written, but this is a little bit more modern than Eddington's book. But it makes no mention of black holes. So in the late 70s, there was a widespread belief still that black holes were mathematical solutions with no physical significance. Students of Chandra's, my friends, would go to MIT and so on and give talks, and people would listen to them politely, but then leading physicists would tell them, you don't really believe them, do you? I mean, this is all mathematics, it's not really physics. It's completely changed now, right? Now, black holes are ubiquitous. I mean, they're everywhere. Every galaxy is supposed to have a black hole in its center. Now, it's a major discovery or a surprise if, in fact, you find a black hole which doesn't seem to have a black hole in its center. So, everything is completely changing. Here is a black hole gobbling up, emitting X-rays as matter falls into it, accelerate charged matter, it emits X-rays. These images are seen. Here are two supermassive black holes. These are black holes in the center of the galaxies, and they are on their way to collision with each other. Here is a gamma ray burst. Gamma ray bursts are the most energetic phenomena in the universe. In a few blinding seconds, more energy is emitted than 1,000 suns in their entire lifetime. And these are seen routinely, once a day or once a week or so. So there are many, many of these objects, and the only way to account for their energy is gravitational energy, namely gravitation. This is not the nuclear energy. Any other processes cannot account for this energy. It is conversion of, it's the gravitational process which actually caused this. So these are really either collisions of neutron stars, which will form such a black hole, or it will be some, it's a formation of black hole of one kind or the other that leads to these processes. Okay, so that brings me to the last part of the talk, which is about gravitational waves. And this is particularly exciting right now as we speak. Now, what are gravitational waves? Literally, they are just ripples of curvature on space-time. Gravity is encoded in the curvature of space-time. Therefore, a wave is the ripple of curvature. So this ripple in the geometry of space-time. Now, you all know about electromagnetic waves, like this electromagnetic wave which is shining up here. And you can work out how they are emitted, right? So you can have a dipole, and that dipole can oscillate. So I got positive charge and negative charge, and that oscillates, and when it oscillates, it produces electromagnetic waves. Well, something similar is true with gravitational waves. Namely, that just as moving electric charges produce gravitational waves, in general relativity, the moving masses produce gravitational waves. So, just as moving charges produce electromagnetic waves, moving masses produce this. Here you need time-changing dipole moments. Here you need time-changing mass quadrupole moments. They come in, the gravitational waves come in two polarizations. If you have a bunch of test particles like that, a gravitational wave passes through, then this ring would be deformed in this way for one polarization, and for the other polarization, it will be reformed in this particular way. And Einstein worked this out just 2 years after the publication of his theory. So it was there. But still, for a very long time, whether there exist gravitational waves in full general relativity remained a controversial subject. And this is because of the following. You see, in electromagnetism, you talk about radiation, and that falls like 1 upon r. But what do you mean by 1 upon r itself is determined by geometry. And geometry itself is a dynamical entity in general relativity. So therefore, there's a confusion. Right? What exactly one means by 1 upon r, and if in fact you have got gravitational waves in full general relativity. And so there was a great confusion until the 1960s, and whether gravitational waves exist in full nonlinear general relativity, or if they are actually artifacts of weak field approximation that Einstein had made. And surprisingly, Einstein himself contributed to this confusion. In a letter written to Max Born in 1936, the famous one of the founders of quantum mechanics, he wrote, together with a young collaborator who was Nathan Rosen, I arrived at the interesting result that gravitational waves do not exist, although they had been assumed to be a certainty in the first approximation. This shows that nonlinear gravitational wave field equations tell us more, or rather limit us more, than we had believed before. In the weak field approximations, linear gravitational waves, they exist, but in the nonlinear full general relativity, they do not exist. It turns out, it was revealed about 10 or 15 years ago, that the paper actually was sent to physical review, and this was refereed, now we know, by Robertson of the cosmologist, and Robertson wrote a 10-page review, sent it back saying that the paper is flawed. Einstein was furious, because in German system, like also in France, and the members, the fellows of the society, just read their papers, and they just appeared in the proceedings. So the proceedings of the Prussian Academy just reproduced Einstein's papers. They were not sent to a referee. He did not know that papers were sent to a referee. And in fact, he wrote an angry letter saying, I send you this paper to publish it, not to show it to other people without my permission. All this correspondence exists. You can look at it on the web. It's very interesting. And then he withdrew the paper and refused to send any other paper to physical review since then. By the way, the same year, he published 2 seminal papers in physical review with Nathan Rosen. One is called the Einstein-Rosen bridge, and the other one is the EPR paradox. It was the same year that these papers had appeared before. And this was the 3rd paper in the series. Well, then he sent it to the proceedings of the Franklin Academy in Philadelphia, which of course immediately accepted it. And it was going to be published. They sent back the proofs. And then Einstein realized in the meanwhile that the referee was right. And he changed the article in the proofs. And therefore, the proof, this conclusion doesn't arrive. In the printed version, the conclusion is not there, that the gravitational waves do not exist. It has disappeared completely in the conclusion. We all know these things because the proofs exist, everything else also exists, and so on and so forth. So, even Einstein makes mistakes. We make mistakes. So, don't be afraid of making mistakes. Of course, don't copy Einstein, make silly mistakes, but okay. So then this confusion was really clear in the 1960s to the work of Hermann Bondi and Ray Sachs. Hermann Bondi had a group in King's College in London, and Roger Penrose, who at that time was also in London. And the reality of gravitational waves in full nonlinear general relativity was firmly established in the 1960s through systematic theoretical analysis by these people. And on the observational side, we know that gravitational wave exists, but only indirectly. Because we have got these double star systems. One is a pulsar, the other is an ordinary star, and they are going together. But they are actually emitting gravitational waves because their quadruple is changing. The quadruple moment of the system is changing as they go around. And one can calculate how much quadruple moment should be changing, therefore how much energy should be lost via gravitational waves using Einstein's formula. And then because they lose energy, they fall towards each other slightly. So one can actually see the orbit is shrinking exactly as predicted by general relativity. So we know that, and therefore that's why we know that gravitational waves exist, and that is the only Nobel Prize for general relativity that was given so far. So we know that they exist. But now the ambition is much more. Namely, the idea now is to detect gravitational waves directly on Earth and create brand new type of observatories which didn't exist before. All the observatories we have so far, all the knowledge about the universe we get is through electromagnetic waves. It could be visible light, it could be infrared, it could be X-rays, it could be gamma rays, but it's just electromagnetic light. Now, with the gravitational wave observatories, they will bring a signal in the form of gravitational waves. So a brand new window on the universe is now available. It's a tool to probe the most violent or energetic events in the universe, such as black hole collisions, supernova explosions, gamma ray bursts, and so on. Gravitational waves will provide detailed images that we cannot be obtained from conventional astronomy. The photons emitted from there scatter a lot and lose their memory. Gravitational waves interact very weakly, and they bring us a faithful picture of the spectacular events that are taking place in the universe. Now, so far, we have got these observatories, as I'll see in a second, but so far they have not detected any gravitational waves. But the observatories are sufficiently sensitive now. Now we do know that there are very, very dense objects nearby in our galaxy, the Crab pulsar. This is the explosion that the Chinese astronomers have noted, occurred in 980, I think, AD. And there is a pulsar, it's a neutron star, it's an object like that. And supposing there was a mountain in the pulsar which is just a meter high. If there is a mountain which is a meter high, then as the pulsar is rotating, the quadrupole moment of that object is changing. Therefore, it should be emitting gravitational waves. The sensitivity of the detectors until last year was already high enough that they should have seen these waves. They don't see these waves, which tells us that there are no mountains or crab which are higher than a meter. I mean, it's amazing, right, that we can put this science together to say what is happening out there in the universe. And that, by the way, tells us something about the equation of state of nuclear matter in the neutron stars. So it's fantastic the way that this science sort of weaves together. Today now, there are brand new types of observatories. In the US, the National Science Foundation has built two. They're called LIGO, Laser Interferometric Gravitational Observatories. And Europe has built one, which is Virgo. And laser beams, what they have is laser beams, which go around 4 kilometers, reflected back, go around 4 kilometers, reflected back. If a gravitational wave comes by, it will shake the mirror at the end of this cavity up here, and that shaking of the mirror will destroy the interference here. Therefore, there will be fringe shift, and we can measure how much fringe shift there is. This is really state-of-the-art technology. One is talking about measuring displacements of the mirror of 10 to the minus 13 centimeters, nuclear radius, right? Radius of a proton. And one can actually do that. The sensitivity now is really, the required sensitivity has been reached now. There is a synergistic interplay between fundamental science and the state-of-the-art technology involving general relativity, astrophysics, statistics, cyber science, high vacuum physics, suspension systems, lasers, and optics. You've got laser beams going 4 kilometers coming back. We've got high vacuum, the highest vacuum that we have on Earth. And now it has reached the desired sensitivity. The engineering runs were finished. The science runs had just begun. And amazingly, you might have seen just last week, there was an article in Nature, almost 2 pages long, which was based on a rumor. At least I had never seen an article reporting a rumor. And the rumor was supposed to be that they might have seen the first gravitational waves. That's why it's so exciting that they might have seen this. And therefore, this is so exciting because it is opening a new window on the whole universe. It might change our view of the universe in a dramatic fashion. And fortunately for us, in fact, there is a golden opportunity for India. India has been invited to join the global network of the gravitational wave observatories. NSF of the United States is agreed to provide an advanced detector of about $80 million. And GAE and DST are supposed to build a LIGO India observatory, which will cost about $200 million. The DAE request is pending at the cabinet level. And this high-profile international collaboration featuring a consortium of national labs and institutions has been formed. It is led by Indigo, which is right here in this institute, by Bala Iyer. And Ayuka is leading the data analysis on exact science. The IPR at Ahmedabad is leading the work on vacuum systems. And RRCAT in Indore is leading the work on lasers here. So this is going to be developing and deploying the highest caliber state-of-the-art technology on the Indian soil to unravel the deepest mysteries all the way from the far edges of the universe. I think this is really an extraordinary opportunity to develop human resources in a variety of cutting-edge fields in pure science as well as technology, and a chance to participate in the front ranks of the greatest revolution that was unleashed by Einstein's ideas. So I really, really hope that this request is granted soon, so that actual work will begin and India will be able to participate in this key moment when the new windows of the universe are getting open. If India is one of the active participants, that would really be fantastic. Okay, so now let me just summarize. The discovery of general relativity by Albert Einstein 100 years ago was quickly recognized as a supreme triumph of human intellect. Paul Dirac, one of the founders of quantum mechanics, called it probably the greatest scientific discovery ever made. For 8 years, 1907 to 1915, Einstein had been consumed by the tension at the foundations of physics. And by not letting go and working persistently, he had to learn new mathematics, develop new concepts, do hard calculations. He discovered a theory that represents an unprecedented combination of mathematical elegance, conceptual depth, and observational success. The process carries many lessons for younger researchers up here. Don't give up. Max Planck comes and tells you you're wasting your time. Don't believe it, right? I mean, if you believe in your idea, then push it. But be your own critic, right? Your worst critic. I mean, try to punch holes as much as possible, not just be blindly follow the idea. And if you don't see anything wrong with it, just pursue, and you might find something fantastic. The decades have passed, and new aspects of revolutionary paradigm continue to emerge. We've seen the Big Bang, the black holes, the gravitational waves. And now a century has passed since Einstein's discovery, and yet every researcher who studies general relativity in a serious manner continues to be enchanted by its magic. I had an occasion to give you a glimpse of bird's eye view of few of the samples up here. There are many, many things that are happening that are illustrated by pictures up here. In particular, there are developments in mathematics I did not go into at all because they are somewhat technical. But general relativity has provided impetus in so-called geometric analysis by providing new invariants of metric manifolds. And this has become a real standard tool in geometric analysis now. Similarly, in computational physics, general relativity, this gravitational wave physics, has pushed the frontiers, really, of computational physics itself, both in numerical simulations and data analysis. And in quantum physics, we're bringing together general relativity and quantum gravity, and cosmology and astrophysics. So there are many, many things that are left out here. If you want to read more about it, there's a volume which was published just a few months ago to celebrate 100 years of general relativity and gravitation, a centennial perspective. It was commissioned by the International Society, and it was released in 2015. And it has 4 parts, and these 4 parts are Einstein's triumph, cosmology, astrophysics, and other applications, gravitational waves, a new window on the universe, mathematical applications, gravity, geometry after all, and beyond Einstein, the quantum physics. Each of these parts has an introduction written by the editors. In about 10 pages, it summarizes what has happened. And so this is really very useful for students and younger researchers. I also want to encourage you to buy this volume, if you can afford it. The reason for that is that editors have donated all their royalties to the International Society to support research by younger researchers. Okay, so now let me conclude. I told you what general relativity feels like. Now, is there one phrase which can capture what those of us who work in general relativity all the time feel about this? And not surprisingly, it is Einstein who his words capture this feeling. I began the talk by telling you about the letter that Einstein wrote to Sommerfeld, telling Sommerfeld that he had just discovered this theory. Einstein apparently writes very, very beautifully in German. The English translation is already beautiful, but in German they are even more beautiful. Sommerfeld was surprised by this exuberance, because it was not characteristic of Einstein to be so exuberant about his own work. The one exception was general relativity, discovery of general relativity. And so Sommerfeld wrote back saying, Einstein, really? I mean, it's really that fundamental? And Einstein's reply was, of general theory of relativity, you will be convinced once you have studied it. Therefore, I am not going to defend it with a single word. Thank you.
So thank you very much again, and please do come again for academy lecture. As an appreciation, we have something.
Oh, thank you.
There is a hot cup of tea or coffee, something in the other side of the hall.